Good afternoon, everyone, and welcome to the first Ventilation Engineering Group webinar. This is our first event, and it actually marks the start of the financial year for Engineering New Zealand. And I'd encourage you, if you're not a member yet, to become a member. And we'll be looking to host more of these events going forwards. This first event is focused on the H1 compliance changes and how they will impact on engineering design for buildings. We have two presenters for you today that will be addressing the building fabric and then the HVAC components. So just to give you a little bit of a background to the Ventilation Engineering Group and in many ways some of the reasons for us coming together and forming the technical group. COVID, of course, was the driver for that. So really putting a focus on indoor air quality, but within that mix and referencing COVID as our sort of kaikoura, if you like, that's really focusing the changes and the role the engineers have to play with indoor air quality. We are looking, of course, at energy efficiency as well. And the focus of this webinar will be on the energy efficiency gains that can be achieved under the new H1 changes. So today we have Karl Wakelin from Aurecon, who will be presenting effectively on the building fabric, on VM1 and VM2, and the changes associated with that energy modeling. And then we also have Mike Gardner from WSP, who will be presenting on VM3, verification method 3 for HVAC considerations. So the presentations will run back to back for about 20 to 25 minutes each. And then at the end of the session, within the 1 hour allowance for webinar, we'll have a Q&A session with both presenters together. If you do have any questions that you really need answering during the presentations, the presenters are happy to take those, but I would ask that we just hold off until the end and then have a more open session. There will be a voting mechanism as well, and I'll address those questions as they come through at the end of the two presentations. So in sequence, I'd like to hand you over to Karl. And Karl, if you could take us away with your presentation, please.
Kia ora, everybody. My name's, as Hugh said, Karl Wakelin from Aurecon, Building Sustainability Leader. So yeah, I've been sort of working in the industry doing building performance work and sustainability work for the last sort of 12 to 13 years. My passion is around building fabrics and building envelopes. And that's what I'm going to touch on today in terms of the new H1 and the changes that means for the building fabrics and how that might impact both architects and ventilation engineers and wider design teams. So I'm going to cover off H1AS1 or VM1 and H1AS2 and VM2. So basically the clause update sort of happened in late last year, and they come into effect on the 29th of November of this year for commercial buildings. And then there is also, as some of you may well be aware, there's a delay for residential buildings that's not till later on next year. I'm not going to get into too much of that detail specifically. The considerations when they did this update was around energy use and carbon emissions, but also health benefits, product availability, and some other aspects like dew point and condensation risk, and also workforce skills, and trying to step there in achievable steps and not trying to jump too far. In saying that, some of the impacts to the industry, some of the feedback we're getting, it is quite a large jump, specifically in the commercial buildings space. So it does also cover alterations and refurbishments, as well as obviously new buildings. Any retrofit or major refurbishment will need to comply, but only in the areas that are altered, or you can look at doing the whole building. This has been rather tricky on a couple of projects we've had. For example, one of them we've actually gone and had a pre-app meeting with council to make sure that our H1 methodology and our process is in line with what they're expecting for this particular building that's going under a major refurbishment. So just something to keep an eye out on. So there's the two different types of buildings, small and large. So small buildings, any housing or any other typology that's less than 300 squares. And then the large buildings are non-residential and over 300 squares. One of the significant changes they've made is, MB have made, is moving from 3 climate zones to 6. This is much more representative of other countries or states, potentially, you know, in the United States, where they have a lot more climate zones to reflect the different climates across those areas. So California, for example, has 8, and it's about the same length as New Zealand, with lots of different climate zones or climates. And so we now have 6 to try and cover those different areas. Part of those changes that they've made is they're trying to move as far and as fast and that is achievable using current products and construction practices. So that really influenced some of the decisions that were made, and you'll see that in some of the R values that they selected specifically in the small buildings. For large buildings, the intent was to move towards a 23% or above a 23% reduction in energy, and then small buildings, they are estimating it's a 40% reduction in energy. So these are the new climate zones. So you can see there's much more granularity now. We've gone from 3 to 6, and the South Island is now broken up into basically 4 separate climate zones. So much more difference across the regions there, and really captures the colder parts of the country. So I suppose the biggest change really is in the window or the glazing performance within both of the areas. So small buildings, you can see there, they've basically tried to have a flatline approach for windows across all of those climate zones, which was, to me, is an interesting decision, but is again maybe trying to link it back to just what's available in the market. That's quite a big jump. That's basically from, in general, most climate zones, you're looking at double glazing, and now you're looking at potentially double glazing, thermally broken, inset windows, and getting the detailing much better than it was before. Windows obviously have the largest impact on your facade, and that's where you should be spending your money, especially in smaller buildings. There is a 2-step approach for the smaller buildings until the 2nd of November of 2023, so you can get away with a 0.37 window, but I would encourage any team to be looking at higher values of performance. And where the impact is for large buildings, it's actually an even bigger jump relative to what it was before. An example is you could get away with single glazing in climate zone 1 before, and now which was 0.16 for an R value, you're now looking at 0.33. So it is a really big jump. What this is going to mean for large commercial buildings is that we're going to need to shift away from highly glazed office blocks or buildings. Anything above 50% window to wall ratio is going to be very difficult to have it achieve the requirements in terms of the reference building using more energy than the proposed building. And if you do have a highly glazed building, then the shading coefficient is going to become very important. You're going to start looking at shading coefficients of around the 0.3, 0.4 mark. And just like in small buildings, large buildings, you're going to be looking towards thermally broken curtain walls, as well as, depending on how much glass you have, an integration of low E and solar coefficients to deal with some of that impact. And in highly glazed buildings, it gets more and more difficult to offset the low performance of the spandrel sections. A lot of those spandrel sections are nowhere near, or what's available in the market is nowhere near what the wall requirement is, which I'll get to in a little bit, which is for Wellington, for example, is R2.7, and most spandrels that we've seen in the market are around about the R1.4 mark, which means they have to work very hard to offset any high levels of glazing. The roof R values have really jumped up for both small and large buildings. Interestingly, on small buildings, they made the decision to go to R6.6 across the entire country. interesting decision, I suppose. They're trying to make it even. Not sure why you have different climate zones if you're going to make the same R value. We have some concerns around just throwing a whole lot of insulation into these roof build-ups and not really thinking about addressing interstitial condensation or vapor control on the warm side of the insulation to mitigate some of that condensation risk. So it's something to think about and feed that back to your clients. We would be recommending that both for small and large buildings to look at warm roofs so that's basically externally insulating your roof to mitigate that risk. If you're doing a cold roof, could be there is some risk involved there if you're not using vapor control and vented spaces above the insulation. To put that sort of numbers around that, R6.6 in a typical roof build up in your attic, say, that's about 500 mils of bats. In a PIR warm roof, it's about 150 mil of PIR, or it's about 250 mil of rock wool. For large buildings, the R values have definitely gone up in the roofs as well, and they actually do step up in terms of the value of their performance across each of the different climate zones. So in climate zone 6, you're looking at an R7 roof, which is approximately 200 mil of PIR. So you're getting some pretty decent build-up thicknesses there, and something that needs to be thought about with your architects and how that looks aesthetically at the fascia and the soffit line. Next one is the wall R value changes. So for small buildings, they decided to basically just have a flat line R2 right across all climate zones. And that was basically based off the fact that it can still work within a traditional timber stick building, and it wasn't going to cause too many issues on a sort of buildability front. I do think it should have gone up in some of the lower climate zones in South Island, but I think that'll happen in the next phase in maybe 2 to 3 years time. In large buildings, like I said before, they have decided to step up the R values in each of those sections. You can see it starts at R2.2 and works its way up to R3.2. Again, that is where in large buildings where you've got curtain walls and your spandrel section is essentially your wall. If it's solid, it's really quite difficult to get that spandrel section anywhere near these R values that are listed here. So something to keep in mind, and then really sort of trade that off with how much glass there is and what sort of performance you can get out of that glass system, or whether it's thermally broken. And really trying to push I suppose the outfits that supply the spandrels. How can we actually bring that R value up as well? And we have seen additional layers of insulation being installed inside those spandrels to try and beef up that performance. Here's some examples of what a wall envelope option might look like. This is maybe more for housing or for apartments, but you're starting to get to some some pretty complex system. Warm wall with 100 mil external rock wool would meet requirements for climate zones 1, 2, and 3. And then if you've right down the bottom, 140 mil stud with R4 insulation will meet it across right down to climate zone 6. Floor R values. So for small buildings, it's changed slightly. It hasn't gone up that much, but basically slab on grade will no longer comply in any climate zone, and your slab edge insulation will be your minimum requirement. We would definitely recommend that for smaller buildings, any slab edge is insulated, as well as beneath the slab as well. And then you can see there's different rates of insulation depending on whether it's on ground or whether it's a suspended floor. Those suspended floor numbers should be pretty easy to hit just with your joist sizes and spacing, and then just specifying higher value bats or whatever it might be in that floor build up. For large buildings, you basically for the most part, you would require slab edge insulation as well. But there's basically these slab to perimeter tables that you can find in the document where you can figure out your slab perimeter to area ratio, and then it will tell you what you need, what you can get away with basically. But for the most part, like I said, unless it's a very large slab, you're going to be doing slab edge insulation at the least. So here's just an example of the tables. There's a lot of different tables in the guidance. And what do we got? Tables. Yeah, and I suppose the main thing is here is from a straight performance perspective and a realistic real world perspective, the tables don't really distinguish between climate zones. So the ground temperature in Queenstown in the middle of winter is a lot colder than potentially what the ground temperature is in winter in Auckland. So just something to consider as you're guiding your clients through some of these decisions. And yeah, like I said, we would recommend under slab insulation whenever possible, and obviously in line with what the structural engineer is happy to facilitate within their design as well. So this is just this next slide is just an example of a passive house comparison to new H1 to the previous H1 for small for housing, but it just kind of, to put it into context, passive house is where we need to be in terms of our 2035 buildings for climate change goals. It's roughly the level of performance. So that's where we're heading to, say in 10, 12 years time. And so that's the blue bars. The green bars is the old building code, and then you can see the new building code has jumped up, reasonably significantly, but still quite a long way away from the passive house levels. And I think the biggest one there is the difference between the glazing, and that's where you'll see glazing performance in passive house buildings is double to triple, sometimes 4 times more higher performing. These examples here of passive house thermal envelope R values, these are real projects that were actually built in these climate zones across the country. So in terms of energy modeling, or the different modeling methods that you can undertake. So for small buildings is the schedule method. So if your glazing area is less than 30%, you can use the schedule method. If it is over shells, and then the calculation method can be used for anything where it is less than 40%. Following on from that, if it gets higher than 50% or higher than 40%, you then need to look at the modeling method. For large buildings, the window to wall ratio, if it's over 50%, you need to look at the modeling method as well. And to be honest, we would, and any project with a curtain wall in it has to do the energy modeling method. And what we're finding is that the energy modeling method is the best way to get there, to actually to tease out how you're going to meet these requirements across the whole form of the building. Last few slides here, I've just got some examples of some of the issues in the industry and some things that we need to watch out for, especially as we start to introduce higher levels of insulation. The building on the left is a new code-built home in Christchurch, so to the old code. But what you're seeing there is basically energy loss through the studs, through the dwangs, through the lintels, and a whole lot of basically the building is sweating. So as you introduce more insulation, you then trap more moisture, and so you need to ventilate, and you also need to introduce vapor control to the warm side of the insulation. The code currently doesn't mandate this, and it's just something that I would definitely encourage everyone to be very, very mindful of. The image on the right is basically a building that was built in Auckland. It's out of lightweight steel. And the same thing's happening. You can see ghosting of the steel through the jib because it's damp. The steel is cold. It's not insulated to the outside, and it's basically there's a dew point occurring between the face of the internal face of the lightweight steel studs or dwangs and the outside face of the jib. So yeah, some real sort of concerning issues there around introducing more insulation and the condensation risk that occurs with that, and the fact that a lot of our homes are not actually ventilated very well to try and mitigate some of that risk at the same time. And another, I suppose, a few other examples in the commercial building space and large buildings is we're going to have to think very carefully about thermal bridging. So the image on the left is a basically a thermal imaging camera or shot of a balcony that is poured as one continuous concrete system from the floor out to the balcony, and you can see it's just losing energy like crazy through there. So we're going to start to think about having thermal breaks or having separate clip-on balconies to address some of these issues. Currently, you don't actually have to cover off you don't have to address these specific thermal bridging areas within your build-up, but that's coming. That's probably in the next iteration. And like I said before, the image on the right, this is an example of a cold roof in a school that has basically the moisture from the students in the space from their breathing has gone up through the ceiling tiles, through the insulation, hits the cold rafters or purlins, condensates because it's less than 12 degrees, and then drips back down onto the students, and they ask why it's raining on a nice sunny morning. So some real risk there with those cold roofs, and again would recommend that warm roofs is the best option and should be option A on all projects moving forward, and mitigates a lot of that sort of future durability and maintenance and roof rework that is happening across the country with cold roofs that were built in the last sort of 5 to 10 years. So yeah, where is this headed? Again, like I said, this is the first step on our path towards the Building for Climate Change framework, which ties in operational energy as well as embodied carbon. Bringing it back to passive house, the image, the 15 there on the far right, the final cap, which is where we need to get to for thermal performance demand in 2035. That's 15 kilowatt hours per meter squared per annum for heating and cooling. And so that's basically passive house. And so, yeah, currently we're probably in the realm of, well, there you go. Our best commercial building that we're doing right now in our modeling is showing around 25 to 30 kilowatt hours per meter squared per annum for heating and cooling loads. But your average building that we're building right now could be at least in the 60 to 80 range, depending on how low performing the facade is. So got a long way to go, and there's lots of details that we need to work through. And I think the big one moving forward is around thermal bridging and reducing window to wall ratios, and detailing of any facade elements like shading and that type of thing, because those shading elements can also start to bring in more thermal bridging as they're connected back to the structure. So that was it from me. Thank you, everyone.
Okay, thanks, Karl. Some particularly good examples there as well, reinforcing the point about thermal bridging relative to insulation from that site from Christchurch. And yeah, thank you for the insights as to the changes that are coming and the journey forwards, really, because it's not a one-stop change. It's an ongoing kind of journey, as you mentioned, with the backdrop of
It's only going to get harder.
More challenging, and yeah, it's our challenge as well as a sector. I think that links also to the ventilation piece in terms of removal of moisture and the importance of those considerations for domestic as well as commercial buildings, and leads us on nicely to Mike Gardner, who will talk a bit more about some of the HVAC side. Over to you, Mike.
Hi. So has that come up okay, Hugh?
Yes, we can see it very clearly.
Excellent. Okay, so yeah, Mick Gardner from WSP, principal engineer in the Auckland team. So earlier on in the year, I got tasked with looking into the H1 implications for our team, and particularly looking at the HVAC requirements under the new VM3. So as a lot of you have seen with the documents that we've gone from one single document to 5 new documents, and the one at the end is the H1 VM3. So that is the requirements for HVAC for commercial buildings. So as you said, it's for commercial buildings. It excludes process and heating requirements in any of those buildings. So things like IT servers that are do not come under the VM3. If you have a building which has both industrial and commercial, say, so you have a big warehouse with a 2-story office on the side, the commercial area will have to meet the VM3 requirements. Whatever ventilation or anything you've got in the industrial warehouse won't be required. So the contents of VM3, they've looked at air conditioning and mechanical control, fans, particularly the energy, ductwork, insulation and sealing, pumps, pipework insulation, for space heating, chillers, unitary air conditioning and heat rejection. They've all looked at COPs and the efficiencies that we have to meet. They've also put items in there for energy monitoring and maintenance access. So the maintenance access will help sit alongside your safety and design requirements. So for air conditioning systems, they are insisting now we have to be able to deactivate, we have to zone systems, control operating times, provide air economy cycles over anything over 2.5 meters cubed, control the central plant, variable speed for fans over 1 meter cubed, and also there's requirements for commissioning. So, I can't read that. So another point on the economy cycle, where you have heat recovery, you must have a bypass to give you that free cooling. And for commissioning, they're talking about you've got to provide plenty of balancing dampers and balancing valves to enable a system to be commissioned. So key points for zoning. So where you're serving more than one zone or area, you have to be able to thermostatically control, not control it by mixing actively heated air and actively cooled air. And there's an item here about limiting reheats to not more than 7.5 Kelvin rise in temperature. That's going to be an interesting one, because a lot of the time when we put air in, particularly if using like a VAV system, we can end up increasing that temperature a lot more than that. So this system here is saying that actually we can't be doing that. It says it limits on the reheating, intended to encourage grouping of areas with similar heating and cooling demand rather than subcooling the air and reheating it. So that's basically like a VAV system. The limit on reheating of systems with a variable supply air rate constitutes an inverse relationship between allowable temperature rise and supply air rate. So yeah, they're basically saying that they're limiting cooling and reheating. So outdoor air economy cycle, as you know, has to be provided more than 2.5 meters cubed, other than where humidity control is required on an air conditioning system. Variable speed fans, again, required for anything over 1,000 liters a second. I think that's going to be an interesting one at the moment. I know there's a lot of issues with availability of fans and control, so we'll see how that goes at the moment. And commissioning, an air conditioning system should be provided with dampers for balancing. Also, variable speed fans ensure the maximum design air or fluid flow is achieved, but not exceeding more than 15% above the design. So, yeah, we can't greatly oversize pumps and fans and just just throttle things down and turn them down as we probably have done in the past. Another key point is that they're talking about limiting outdoor airflow. So anything over flow rate of 1,000 litres seconds shall have demand control. And also they're talking about having energy reclaiming systems greater than 60%. So a note on here is that you are not to exceed any of your airflow requirements by more than 20%, except if the air is unconditioned, so using free cooling, additionally required to balance any other process things, or if you are using heat recovery of more than 60%. So this is getting quite interesting with a lot of the stuff, a lot of talk of COVID, because there's people are starting to use higher airflows sometimes. I've been looking at higher airflows, and also with Green Star. So with Green Star, you know, if you're Green Star 4, you need an extra 50%. Green Star 5, you need an extra 100%. So if you're going Green Star now, you'll be forced, could be forced down the path of having to use heat recovery purely to comply with Green Star. So one thing they've introduced now is a calculating for fan efficiency for fans, or motor efficiency for fans. And being from the UK, obviously I've gone through with Part L on the requirements we've had to do for that, where we've had tables. It's all been tabulated on the fan use, and whether it's an air handler unit, and it gives you a targeted specific fan power. Here you have to calculate the required fan power based on the design of the system and the type of fan you're using. So it's getting a bit more complicated. They've developed 4 arrangements for a fan. So you've got, for example, a type A, in this arrangement where a fan is installed with a free inlet and outlet conditions. So that's like a window or wall fan. Type B is an arrangement where fans installed with a free inlet and ducted. So, yeah, and then they're building up like that. So types A and D, which are with no duct, or type D is an arrangement where the fan is installed with a duct fitted to its inlet and outlet, can use the calculation equation 1, which is quite a simple calculation. You just need to your pressure of the system and calculate it that way. When you get into equation 2, which is where systems have a great static pressure above 200 pascals, you go into equation here where you'll be using the fan motor power, and then there's a series of coefficients which are provided within the guide, and they got put into this equation. So I'll show you so this is a table at the moment. So you have a selection of different fans you can use, axial, centrifugal, and also you correlate that with your installation type, either A or C or B or D. So this will then give you all these coefficients that get inputted into the calculation. This fans that are exempt from this, you do not need to do this for smoke extract. You do not need to do this for kitchen exhaust fans or anything with a processed specialty like fume cupboards or anything like that. And you also do not need to apply this for any fans that need to be explosion proof. Included within this, the brought in rules for ductwork. So your pressure drop across your index run has to be calculated, and you must not exceed 1 pascal per meter of pressure loss as you're sizing your duct as an average over the entire length of the duct. Pressure drop for flexible ductwork sections may be calculated as if the flexible ductwork is laid straight. So we are assuming that when we are sizing this, that the ductwork It's laid nice and flat, not crushed like we sometimes get on site, and it's all been laid nice and perfect. They're also now saying flexible ductwork must not exceed 6 meters in length in any duct run, which is still quite a high run. Upstream connections of ductwork bends in the index run must have equivalent diameter to the connected duct, and turning vanes must be included in all rigid ductwork elbows of 90 degrees or more acute than 90 degrees in the index run, except where there's a fouling risk or long radius bends are used. They have provided some maximum pressure drops for some specific fittings, so anything across a coil. They've got a maximum clean filter pressure drop. So when you're looking at fan coils and HUs, a lot of this we'll be speaking to manufacturers, but making sure that we're not exceeding these pressure drops in any of your equipment. And also they're now bringing in more requirements for duct insulation. So this will be all stuff that's included in your specifications. So we're complying with AS NZS 459.1. We've now got our values greater than or equivalent to 1 meter squared kilowatt per watt, and for cushion head boxes, connecting ductwork, and for rigid ductwork, fitting specified to table 5.2.1.1. Also, that the insulation is protected against the effects of weather or sunlight to reduce the likelihood of affecting the poor insulation properties over time. So that's now a requirement. It is installed so that the butts joint installation to form continuous barriers, maintain its position and thickness other than flanges and supports. And where conveying cooler air, we've got our vapor barrier protection. The vapor barrier is a membrane installed so that adjoining sheets of the membrane overlap by at least 50 millimeters and are bonded and taped. So this is all things that need to be incorporated into specifications so that the contractors know what they're doing. And here, just here's an example of some of the R values that we have to comply with. Also, we're looking at pipework pressure losses. So they're looking also at pump motors, because pumps and fans are always constantly running. So we've got to verify the design of the pipework. So in a pipework system that do not have branches and have the same flow rate through the entire pipework network, achieve an average pressure drop in straight lengths along the index run, not more than, and then there's a series of tables, so they're on the next slide. Then any of the pipework will achieve an average pressure drop in straight segments along the index run of not more than, and then again, some more tables. So as we look through here, we've got a series of tables. I've not got them all here, but just as an example. So maximum pipework pressure drop. So non-disruptive constant speed systems at the top there. So depending on the size of the pipe and also your system operating hours per annum, you'll be looking at 400 pascals per meter. As the pipe gets bigger, on greater running hours, it drops to 350 or into 200. So we've got to bear this in mind when we're sizing pipework now, especially if you've got a long running system that's 24 hours. As your pipework gets bigger, you're going to get more restrictions. So this is going to increase pipe sizing. And some more examples there on the different types of systems. So for chillers, we now have minimum COPs to achieve. Now a requirement of H1. I've spoken to a few suppliers on these, and they're quite comfortable with these because a lot of our equipment is already designed to meet some of the requirements for over in Europe. So depending on the type of chiller you've got, you will have minimum COPs to meet. Other bits and pieces that we've got to look at are facilities for energy management. So metering requirements for buildings 500 to 200 2,500 meters squared, and buildings over 2,500 meters squared. So we need maintenance access, required for maintenance and commissioning. Also, we have items for cooling towers. So cooling towers now have to have fan efficiencies. As you can see there, whether it's induced draft or forced draft. And that is it on those items. I'll hand you back to Karl. Oh, sorry, Hugh.
Thanks for that, Mick. Thank you for the run through. Yeah, very, very insightful overview. Thank you for that. Interesting to see some of the ductwork provisions probably aligned to good or best practice anyway, effectively. But interesting to note the cap effectively on the amount of outdoor air that can be supplied as a range. And I think that's probably going to drive perhaps more consideration of the HEPA filters and MERVs and the like.
Yeah, especially like with Green Star becoming a bigger requirement. You know, if you're going for the credit, some of the credits where you need more air, you're going to go straight over that 20% straight away.
That's going to be a challenge. Whereas some of the other items are really just enforcing good design practice in a way across the board. Yeah, so that's going to be an interesting one to look at holistically as to what that does within a COVID or indoor air quality consideration. And as you mentioned, Green Star. Okay, well, thank you very much, both of you. We're on time. We have slightly over 15 minutes for Q&A. Haley, are you able to provide me with the questions that are coming through, and we'll take a look at those? I've got them here, thank you. Okay, there's 5 so far. So if you do have any other questions now the presenters have concluded their presentations, please put them in the channel. So I'll just go from the top of the list. And the question really sort of pertains to the multidisciplinary aspect of this course, and who's responsible for H1 calculation. So is it the mechanical engineer, is it the architect, or the electrician? And the question considers it should be the architect, because effectively they're responsible for the building envelope. But over to both of you for your views on that.
Well, yeah, I mean, I think traditionally it has been, and especially in
your microphone's high, Karl. That's high up on your head.
Oh, there you go. So thanks, Mick. So yeah, traditionally it has been sort of thrown into the court of the mechanical engineer to do the H1 analysis, and I think that's probably still going to be the case. However, much earlier involvement and a lot more sort of very serious discussions with the architect very early on, as early as possible, to be honest, around the intent of the project, the massing, and what it's actually going to look like, ideally before resource consent, that type of thing, so you can actually check that it's going to comply. What we're doing currently on projects is we're actually doing H1 calcs in prelim design at 50% as early as possible, especially when they're highly glazed, and we're quite concerned about the outcome. Traditionally, that was done a lot later down the track, maybe during developed or even detailed design, because it was so easy to get there. It wasn't such a, it wasn't as difficult as it is now. So, yeah. So I don't think the architect's going to be doing it. To be honest, the education piece for architects needs to grow quite a lot in this space.
Yeah, so it's an area where mechanical engineers need to take the lead effectively across that sort of integrated design, and yeah, to address it early on. Yep, either the mechanical or the building scientist, or even maybe the sustainability people. They might be all part of the same team, but yeah, ideally this would be being raised by the full multidisciplinary approach. Everyone should be aware of this, because it impacts everybody, and yep, you know, not just performance, but you know, cost and buildability and all those other factors. Yeah, so it's really increased that emphasis on the multidisciplinary that has always been there, but it's more crucial now. The next question was asked during your presentation as well, Karl, and I think it really pertains more to your piece. and it's asking, is there a method or formula to calculate the H1? I say that because I think that with the verification method that Mick ran us through is quite prescriptive, but when you're looking at the facade, what would you say is the method or formula to calculate the H1?
Well, there's a methodology that comes with it, but it's basically you're modeling up. If you're doing the modeling method, which most of us are probably going to be doing, you're basically building a reference model, a computational reference model of the building, which is based off a 50% window to wall ratio and your sort of schedule method levels of insulation within your wall, your roof, your glass, and everything else, and then you compare that against your proposed design, which is whatever window to wall ratio of your actual design, and then you must just prove that your proposed building uses less energy than your reference building.
Okay, thanks for that. The next question is really touching on the role of local consenting authorities in the process. So questions asking who's designing the requirements? Is it between Engineering New Zealand and the council? Well, this change has come from MB, but in terms of the application of it, perhaps you could both just address the considerations of a designer submitting to council and how you see that playing through in the early stages.
I think I've recently gone through a few rounds with PMs on this. That MB is the main authority on this, and sometimes councils get it wrong, and we need to make sure, as professionals, we're doing it right. I know there was some argument quite recently about, when's this H1 coming in? There's all sorts of dates flying around, and I just had to show them, here's the MB document, this is the date. Ignore whatever the council says, they cannot push it back. So we obviously, the council review it and they go, it's for them to award a consent, but don't forget, it doesn't give us any relief from anything. We are still responsible. And coming back to similar sort of question, like you said, who does the H1 calc? Traditionally it's been the mechanical guys for the thermal envelope. Now we've got all this VM3 stuff in. That needs to be included in your H1 report, because you'll be having to tell the council how your HVAC system is complying. So that all needs adding in, and how we do that is, what might just be, and we do a H1 report, which sort of goes through all of the thermal envelope, and we potentially will have to do something similar, maybe even tabulate, here's all the fans, here's the calculated efficiency, and here's what we've actually got, just to prove it.
So it could be amended multiple times as the occupancy and design intent changes. Yeah, okay. The next question is a bit more specific about the acceptable solution to and calculation method, and listing off the clause there, 2.13.11, and effectively the reference to skylights and roof and floor systems to meet the R values. It's really, I think the person asking the question is just querying the sort of restrictions there on the flexibility that can be applied. Any thoughts
around the area of skylight? Because basically, as I understand it, you're allowed depending on your building footprint and your reference building, you're allowed a certain size of skylight, which then means if you've got a proposed building with a large skylight, it's going to be really which is much bigger than what you're allowed. You really start to get stung for the low performance of the skylight within the proposed building.
So that comes back to your point about changes to glazing, effectively. So
but skylights, skylights are 3 times worse than windows because of the nighttime effect, and when you have a clear cold night like last night, they lose an enormous amount of energy. And as I understand it, I think there's a proposal in the EU to ban certain sizes of skylights in new buildings in the next sort of 3 to 4 years. So that's just an example of where the EU is going.
or to have some covering that could be
Potentially, yeah.
at night. Yeah. Okay, so that's a good point. That's extreme case at night time. Yeah. Okay. Thank you for that. The next question is coming back to council's role about producer statements for H1. I think the question is really sort of emphasizing, do we see a need for more requirements for producer statements around H1, whereas typically it might just be G4?
Not sure on that one, Mick. Have you got any ideas?
So in the H1 I mentioned, it does call for demand control. So one of the ways to do that is for CO2. You could also use occupancy sensors or something like that. So it requires demand control. That is one way of doing it. It doesn't say you must use CO2 control, but if it's asking for demand control, there's only so many ways you can do it.
Okay. That links nicely on to the next question.
That was it, yeah. So,
CO2 requirements addressed in the code.
Yeah. That's what I was reading, sorry.
Oh, sorry, the previous one, the question was just asking about, do we think that councils will typically be requiring PS1 for H1 across the board? And potentially,
Auckland will.
Yeah. So they already do.
They want producer statements for everything. So
yeah.
We've had to produce H1 producer statements on some old projects here, but I think that I know a lot of time we produce like I said, a H1 report. We'll just have to add a HVAC section into that when we're doing a commercial building.
Yeah, and then the question was about who would sign that off. So it does sound like it would be the building scientist or the mechanical engineer. So that
I think that's why we do a H1 report, because obviously we're not going to sign a producer statement for the architect's design.
Yes, so you just limit the scope.
But for the HVAC, we do a producer statement or just HVAC, or do we just include it in the report, but where we have to clearly show how we've complied? So
potentially there could be two statements. Okay. And perhaps we may see councils even pushing for PS2s, as perhaps unfamiliar with the requirements to start with.
Yeah.
But interesting space to watch. And I think you're right in terms of talking with PMs, it's probably is getting in early on the project and allowing not the additional design fee, but some of the requirements through the consenting phase as well. I think you have touched on the CO2 requirements there.
Yeah.
Okay. This next question is about insulation through opening, and it can be compressed. Might need some clarifications on that.
There's no mention of it, so I would assume for energy efficiency, no, they want it keeping nice and uniform all the way through.
But it'll come down to the modelling, I suppose. You just need to account for that and change performance. Okay. Installation of air conditioning to parts of an old building. So yeah, you did touch briefly on sort of existing buildings. So this is for retrofit then of air conditioning to an existing structure that wasn't previously heated or cooled.
So one of the things that I've sort of picked up on the H1 is there's no separation between a new build requirement and an existing building. If you go back to Part L in the UK for specific fan powers, you had new build and an existing building refurb, which gave you more allowance because knowing you'd have more constraints in a refurb. So they haven't given any allowance for that in the new VM3, which I think is something they should look at. And I think an interesting point we were discussing before the presentation, one of the good things that Part L in the UK did was on a refurb, insist on consequential improvements. So if you're doing a refurb, you have to spend 10% of your budget improving the energy efficiency, which I think is something they've missed, and they should bring that over.
Yes, because there's a carbon with that work. Yeah.
Yeah, and I think it's a really good point, especially in the space in our seismic upgrade space. And I think from the murmurings I hear in MB, Mick, I think that's coming probably in the next stage.
Yeah, it
So
is a great thing.
So that's for VM3, but Karl, what about the need to address the facade when introducing HVAC to a building that perhaps doesn't have it? So a conversion of a space.
Well, right now that's not
not required
unless you're touching that facade, and often, I mean, well, not often, but a fair bit of the time, there's the heritage element as well, where they can't actually do much to the facade anyway. They'd have to do it internally and be visually unchanged.
So the answer is, as long as you don't touch the facade in any way, shape, or form, it's just VM3 considerations for HVAC design. But if you do touch it, you own it effectively, and that would be the additional requirements there. So important consideration.
Yeah, as we understand it, the portion of the facade that you do touch has to then come up to the level of performance, but then it's a bit unknown as to where you go to from there in terms of the modeling of the entire building, and then showing that your new proposed building is using less energy than your existing building from before without those changes. It gets a little bit complicated, and the guidance is not very clear, and that's why we've basically approached it by having pre-app meetings with council to try and address it on a case-by-case basis.
Very good. There's going to be a lot of detail on that going forwards. And there's a sort of additional point there about would it be covered already under Section 112 of the Building Act. I think that's almost a topic for another presentation, actually, in terms of looking at retrofit to spaces, because it is a lot of the work that's out there. And as you mentioned, it could be triggered by seismic strengthening and other work. So it's probably another presentation. Last question. This is about the cost of systems, and I guess these do raise the bar, and so some of the VM3 points that you raised off do bring design requirements up to what would be sort of good best practice anyway, and there could be a sort of a learning curve for cost estimators. So the question is, as the cost will increase with a sort of change to code, and QS are perhaps not necessarily that but well placed to account for that. What are the thoughts on designers sort of leading earlier in the process to create awareness and guide the process around the H1 changes?
Yeah, I've on a recent job had to advise the QS saying, look, we're going to go down the new H1. I've got to ducts bigger, we're going to have better performing insulation, potentially pipe sizing will be affected, all these things. But I think that's the main one, is the duct sizing, and again, working with the early on with architects, if you've got this coming on, to make sure you've got the right riser space and the right ceiling space, knowing that your ducts probably going to be a little bit bigger than what you've been doing in the past. We've got to take all these things into consideration. I noticed it was Martin that sent that question as well. So,
and I'd second that. The space that's required for just pipe work that's got extra insulation on it, and just the coordination through through different structural members, and as we start to look at more timber buildings and what the impact there might be, something to really consider early on.
And potentially a subject of another presentation, perhaps with design versus a reference or something like that, to look at the uplift in costs and those considerations versus the long-term operational costs, perhaps, which is where the gains are achieved. That's 1 o'clock, and that's all the questions. So I'd just like to say thanks again to you both. Very insightful presentations and timely. And hopefully of value to everyone. So thank you very much for participating in the first webinar for the Ventilation Engineering Group. Do check out our page on Engineering New Zealand and take advantage of the discounted membership, which is available for this financial year. Okay, thank you very much. Back over to you, Hayley.
Thanks, everyone.
Thank you.
Ka kite.